In this video, we will discuss non-uniform circular motion. This is when an object moves in a circle and changes speed. So as the object is moving in a circle, it's speeding up or it's slowing down. So what causes an object to speed up or slow down? Well, acceleration. But in non-uniform circular motion, we have three types of acceleration to discuss. Let's start with centripetal acceleration. You can see in our diagram that this acceleration vector points in towards the center of the circle. And centripetal acceleration is what causes an object to change direction. Next we have tangential acceleration. And tangential acceleration causes an object to change its speed. This acceleration vector is perpendicular to the centripetal acceleration. Finally, we have the angular acceleration. This is the acceleration that causes the object to change its angular velocity. And remember, angular velocity has a symbol omega, and we can find the angular acceleration from the change in the angular velocity divided by the change in time. This is in contrast to the tangential acceleration, which we can find from the change in the object's linear velocity divided by the change in time. And we can relate the tangential acceleration to the angular acceleration using this equation, which says that the tangential acceleration is equal to the angular acceleration times the radius of the circle. Now that is how you find the angular acceleration and the tangential acceleration, but what formulas do you need to solve non-uniform circular motion questions? Well, what's really cool about non-uniform circular motion is that the equations look very similar to the kinematic equations. So we have the final angular velocity is equal to the initial angular velocity plus the angular acceleration times delta t. And comparing this to our kinematic equations, we see that this is just the Vf is equal to Vi plus a delta t equation. Next, we have the final angular velocity squared is equal to the initial angular velocity squared plus 2 times the angular acceleration times the change in the angular position. And this is comparable to the Vf squared is equal to Vi squared plus 2a delta x kinematic equation. And the final equation says that the final angular position is equal to the initial angular position plus the angular velocity times delta t plus 1/2 the angular acceleration times delta t squared. And this is just like our xf is equal to xi plus vi delta t plus 1/2 a delta t squared kinematic equation. And now in these non-uniform circular motion questions, a lot of the time you are asked to find the number of revolutions that the object does as it's speeding up or slowing down. So if you're asked to find the number of revolutions, use this equation, where the number of revolutions is equal to the final angular position divided by 2 pi. And those are the main equations you will need to answer non-uniform circular motion questions. Let's jump into an example to test your understanding. In this question, we are told that a 10-meter diameter merry-go-round is initially turning with a period of 6 seconds. The merry-go-round slows down and comes to a stop in 30 seconds. And we want to know how many revolutions does the merry-go-round make as it stops. Now we know we are solving for the number of revolutions. So we have to use the number of revolutions is equal to the final angular position divided by 2 pi. That means we need to solve for the final angular position. And so what I've done is I've wrote out our non-uniform circular motion equations, and we want to decide which equation should we use. Now we want to use either of these two equations because they include the angular position. But we have to make sure we have all the variables within them. Well, we can figure out the initial angular velocity because we were given the period. And angular velocity is equal to 2 pi divided by t. All I have to do is plug in the period, and we find that the initial angular velocity before the merry-go-round starts to stop is 1.05 radians per second. And we also know the final angular velocity, and that's equal to 0 radians per second because the merry-go-round comes to a stop. Now that we have the initial and final angular velocity, we can use the fact that the angular acceleration is equal to the change in angular velocity divided by the change in time to find the angular acceleration. All we have to do is plug in our values and we find that the angular acceleration is equal to negative 0.035 radians per second squared. And finally, we can assume that the initial angular position is 0 radians. And with that, we have everything we need to solve for the final angular position. I'm going to use this equation because it's already isolated for the final angular position. So all I have to do is plug in my values and solve for the final angular position. And what we find is the final angular position is equal to 15.75 radians. Now that is not our answer because we need to find the number of revolutions. So we need to plug that answer into the number of revolutions equation. And what we find is the merry-go-round does about 2.5 revolutions before coming to a stop. And that is the end to this lesson on non-uniform circular motion.